Hello, I'm Baman Haji from On Semiconductor. Today I'll be speaking to you about the great wavelength debate, which will prevail for automotive LiDAR. This is a presentation that I originally gave at the Automotive LiDAR 2019 conference in Detroit, and it's been updated and I'm recording it now in September of 2020. So with that, I want to start by talking about the state of the LiDAR industry. There's a lot of innovation happening simultaneously at companies around the world, and there's a lot of different approaches to the technology with cost and performance implications. And in just less than a decade, you've gone from fewer than 30 companies to more than 100 in this industry. So am I talking about the automotive LiDAR industry today? Or am I talking about the autonomous vehicle industry today? Well, actually, this was the state of the automobile industry in 1900, at the turn of the century, believe it or not. All of that is to say that LiDAR is an exciting field, and there's many innovators in a crowded ecosystem. You can see that by the number of investments having gone from less than 50 million to 1.5 billion in just 6 years. And the market size for this sensor has increased from 200 million to projected to be over 6 billion in 2025. So it's obvious that consolidation is inevitable when you have such a vast field with so many different players. And there are going to be winners and losers. Who will succeed? Well, one of the big dichotomies in LiDAR is the wavelength of choice that's used in these systems. And so I'd like to spend the next 30 minutes talking to you about this great wavelength debate between the near-infrared spectrum, like 905 nanometer, and shortwave infrared spectrum, like 1550 nanometer. So we'll go over an overview of LiDAR systems and a market map. We'll do a deep dive on the technology behind LiDAR that has implications on the great wavelength debate. And I'll leave you with a summary of the discussion and an outlook for the future. But first, a little bit about On Semiconductor. We're a Fortune 500 company headquartered in Phoenix, Arizona that was originally part of Motorola and was spun off in the year 1999 and went public in 2000. We've grown organically and through acquisitions. I come from the SensL division of the Intelligent Sensing Group, which is one of our business groups that has product offerings consisting of sensors for cameras, radar, and LiDAR. And as you can see, automotive is our largest sector when you look at revenue. So an autonomous perception system requires LiDAR in the complete suite of sensors, which includes imaging and radar and LiDAR. The reason for this is that LiDAR gives you a high-definition depth map of the surroundings. And if you look at some typical applications for autonomous systems, like in robotic transport and in level 3 to level 5 autonomous vehicles, almost in every case they're using a suite of sensors which includes cameras with CMOS image sensors, it includes radar, and also LiDAR. The data from these sensors is used together to make decisions by the autonomous perception algorithms. This is what's called sensor fusion, but I'd like to describe to you what that means. So, sensor fusion is the combination of these different sensor modalities to be able to provide color and intensity information, depth information, velocity information for every point or kernel in the scene across all conditions. What this gives the perception algorithms is redundancy and the benefit of higher confidence decisions because there are unique advantages with each type of sensor modality. Cameras, radar, and LiDAR are each good at specific things, and working together, the algorithms are going to be able to take advantage of all of that data coming in. LiDAR is particularly good at giving a high-resolution depth map of the surroundings to the autonomous perception system, and that's why it's such a critical sensor. I'll now give you an overview of LiDAR, including a market map of the LiDAR manufacturers. The simplest way to think about a direct time-of-flight LiDAR system is that you're sending out a short pulse of light starting a stopwatch, and then waiting for a photon from that same wavelength that you sent out to come back and be detected by your receiver. And that's a single point, and what you're going to be doing to get a 3D depth map of the surroundings is scanning that beam around the scene. So in a LiDAR system, you have 6 major hardware functions: the transmit, the receive, the optics, the beam steering, the readout, and the power and system functions. As you can see, Semiconductor provides components for several parts of a LiDAR system, but what I'd like to focus on today are the pieces that have implications for the great wavelength debate, specifically being the illumination sources and the receivers, or the detectors. Now recall that I mentioned that LiDAR was a crowded ecosystem of many different companies. And as you can see here, there are some companies that are focusing on being component suppliers on the transmit, receive, or beam steering or readout side, but a larger number of companies are actual manufacturers of LiDAR sensors. Some of these companies have partnered up or been acquired by larger companies that are established automotive tier 1s, and some of them are choosing to take their IP, which may have to do with one part of a LiDAR system, for example the beam steering, and build on that to sell a LiDAR module into the ecosystem. But what I want to focus on next is what wavelength of operation are these LiDAR manufacturers at? And when we break them down by that, we actually see that about 3/4 of them are operating at the near-infrared wavelengths as opposed to the shortwave infrared wavelengths. And furthermore, about half of the ones that are operating in shortwave infrared are using the direct time-of-flight principle, which means that if they have IP to do with readout, for example, it's completely analogous to being able to operate in a near-infrared wavelength. And the remaining ones that are in the shortwave infrared space that really need to stay there are the ones that are doing coherent LiDAR, which is different from the concept that I described with direct time-of-flight LiDAR. Coherent LiDAR has some advantages in being able to give you velocity information, but it's further out in terms of getting to market. So I'm not going to delve into that topic further today, but I wanted to give you that background. Now, when we think about the OEMs, the automotive vehicle manufacturers, and what their requirements for LiDAR are, they don't actually care what wavelength you're operating at. They just want to have an autonomous perception system on their vehicles, right? So what do they actually care about? They care about cost. LiDAR has traditionally been an expensive sensor, and it's still more expensive than the other types of sensor modalities that we described. But the cost needs to keep coming down for higher volume adoption. They also care about reliability. They have automotive grade quality and reliability expectations, and that comes as something that has to be learned over time, especially by smaller companies that are trying to operate in this space, which is why you see a lot of partnerships between big tier 1s and smaller LiDAR manufacturers. And finally, the performance is important. You need to be able to detect small, low reflectivity objects with your LiDAR system in order to be able to be beneficial to the autonomous perception suite. And the other thing to note is that you do have short-range and long-range LiDAR in an autonomous perception system for a level 3 to level 5 vehicle. Just like you have near-range surround view cameras for parking assistance and long-range cameras for advanced driver assistance systems and highway autopilot, you're also going to have short-range LiDAR and long-range LiDAR, and some of those things may change based on the system specification. Now let's get right into the great wavelength debate. So, as you saw, the vast majority of LiDAR manufacturers are operating in the near-infrared space. And as you may have guessed, this has to do primarily with cost. So when you look at what is required in a near-infrared LiDAR system, the detectors and lasers are much lower cost, and we'll get into why. And as a result of that, the supplier ecosystem is much more developed, and the types of detectors that you have in a near-infrared system allow for further integration and a further path for cost downs. Now, performance is the other key thing that you have to look at in the great wavelength debate. And from a system performance standpoint, near-infrared LiDAR systems can still operate with good ranging performance at eye-safe laser levels. And they can do that across adverse weather conditions. So these are some of the reasons why the manufacturers choose to operate in the near-infrared spectrum, and I'm going to now give you more details on why from the ground up. So for the deep dive, we're going to start with some background physics, then we're going to talk about the detectors and emitters, and then I'm going to get into what the eye safety specifications are for shortwave infrared and near-infrared, and show you some system performance simulations and cost implications that lead us to the conclusion. So we'll start with the light and semiconductor physics background. First, you have to look at the atmospheric absorption of light and the impact on LiDAR to see why a manufacturer makes the choice that they do with respect to wavelength. Well, if you look at sunlight, you have at 1550 nanometer about 1/3 of the spectral irradiance that you have at 905 nanometer. That means there are 1/3 the number of photons at 1550 nanometer that can interfere and give noise to your LiDAR sensor than there would be at 905 nanometer. And that has to do with the emission of solar radiation and then its absorption through the atmosphere and what's actually seen at ground level. That's definitely an advantage for a 1550 nanometer based system from a performance standpoint, having less noise interfering with your sensor. Now let's get into the semiconductor light detection basics. In a semiconductor, you have a band gap that separates the valence and conduction bands, and the material is non-conductive unless there is energy to help an electron overcome that band gap. And that energy can be provided with a photon. So a photon has energy related to the wavelength of light that it's coming from. And at the same time, the band gap of the material is related to its sensitivity. So that means that in order for a semiconductor to become conductive, to have current pass through it, you need a photon of the right wavelength to hit it. And now you can see why there might be different types of material required for different wavelengths of operation for a detector. And when we look at silicon, which is the most common type of semiconductor used across the industry, it's sensitive to visible and near-infrared wavelengths, 400 nanometer to 1,000 nanometers. But it starts to be completely transparent beyond 1,000 nanometers. So if you want to operate at 1550 nanometer, you're going to need to do some band gap engineering. You're going to have to alloy these more exotic 3-5 semiconductors like indium gallium arsenide, and then you can make your process sensitive to the shortwave infrared wavelengths. And you can see that on the graph in the bottom right of the slide. Now let's talk about laser light emission basics. LASER actually is an acronym for light amplification by stimulated emission of radiation. What this means is that there is a material called a gain medium where we're going to pump energy into it, and that energy is going to excite atoms in the material, causing the atoms to go to a lower energy band, emitting an identical photon. And when that happens repeatedly, when you replace reflectors on either side of the gain medium, this process happens repetitively and you get a coherent light beam out of the gain medium. Now, if we use a semiconductor as the gain medium, we can actually pump energy into it by putting a bias voltage on the semiconductor PN junction. And the current through the PN junction causes a resonant emission of photons with the laser beam output coming out the side. What's important to note is that direct bandgap material has to be used for light emission, like gallium arsenide, indium gallium, and indium phosphide. You can't use indirect bandgap material like silicon because it would not be as efficient for the atom to fall to the lower energy level. Next, let's dive deeper into the detectors and emitters used in LiDAR systems. Early LiDAR detectors used pin photodiodes. These are detectors that have no inherent gain, and as a result, you're not able to sense weak signals using the detector. And they operate in linear mode, so their output is going to be proportional to the signal that comes in. So LiDAR systems moved on to using avalanche photodiodes, which actually do provide a moderate amount of gain. These avalanche photodiodes are PN junctions that are biased at almost the breakdown voltage, which is how they get that moderate amount of gain from a photon coming in. But they also have wide junctions and use high bias voltages of up to 250 volts. And they're still operating in linear mode because that's still not a lot of gain to be getting on the sensor. So as a result of that, the market adoption of avalanche photodiodes and avalanche photodiode arrays has also been decreasing in favor of higher performance, more sensitive detectors based on single photon avalanche diodes, or SPADs. SPADs are actually avalanche photodiodes which can operate with a low bias voltage, but built in such a way that that low bias voltage of about 30 volts is actually above the breakdown voltage of the device. And what that means is that the device is in a very unstable state where a single photon will cause a massive avalanche multiplication effect and give you a gain on the order of 1,000,000. So now you pair the SPAD with a quenching resistor, which will take the current that's generated and cause a voltage drop to happen, which resets the SPAD into the ready state to sense the next photon. So you have a very sensitive detector whose output will effectively be a pulse every time it senses a single photon. Now you can build arrays off of these SPADs, and what you can also do is combine them into a photomultiplier. A silicon photomultiplier array is an array of these SPADs where every SPAD is operating in parallel. So now you can get an output pulse from a single one of these, or you can get an output pulse based on multiple SPADs firing at the same time, and the output level will be proportional to how many photons actually were detected. So the market adoption for SPAD-based detectors is increasing due to those inherent advantages. Now, what's the relevance to the wavelength debate? Well, you can build these types of devices, these PN junctions and avalanche photodiodes and SPADs, based on silicon, which would be responsive to NIR-IR, or based on 3.5 semiconductors, which would be responsive to shortwave infrared. But manufacturability and cost is the key to viability. So of course, silicon-based detectors are going to be much lower cost, and they're going to be more widely available because you're leveraging the semiconductor industry's years of R&D and the foundries that are already available. And so that's why silicon photomultipliers and silicon SPAD arrays are being increasingly adopted for LiDAR, whereas there are not that many 3.5 semiconductor-based SPADs out there that can be used in LiDAR systems. So this goes to the point of the ecosystem availability. Also, using a silicon-based detector, you have a path to integrate readout logic onto the same chip because it's CMOS silicon technology. If you use a 3.5 semiconductor like InGaAs for your detector, and then you want to have a CMOS silicon readout chip, you're going to need to bond two very different technologies, which also adds cost. Now, InGaAs-based photomultipliers and SPAD arrays, as mentioned, have yet to be commercialized, and there is some R&D on being able to use germanium, which can be sensitive in the shortwave infrared space, and bonding it with silicon, but these are R&D activities, so they have also yet to be commercialized. Now, what about the different types of emitters in LiDAR systems? Well, you generally have two types. The first are edge-emitting lasers. Edge-emitting lasers are very popular today. They're lower cost and they have a very high output power efficiency. But they're more difficult to package because the beam comes from the edge and the beam is actually elliptical. And due to the fact that the beam comes from the edge, it's more difficult to build arrays of the lasers, which can be important for a LiDAR system. And heating also causes a wavelength shift to happen, which is not ideal because it means that on your optics, on the receiver side, you have to have a wider bandpass to accept those photons across the temperature shift. But there's good ecosystem availability for edge-emitting lasers on both the near-infrared and shortwave infrared space. Having said that, the market adoption of edge-emitting lasers is decreasing because there's a newer type of technology called a vertical cavity surface emitting laser, or VCSEL, that's becoming more popular. VCSELs have a lower output power efficiency and they're higher cost, but they have a beam that comes through the surface, and as a result of that, they're easier to package, it's easier to build them into arrays, and they're much more stable over temperatures. They also have a symmetrical beam. So all of these advantages are why the market adoption for VCSELs is increasing, notwithstanding the fact that there's a little bit of a ways to go in terms of increasing the power efficiency to be able to achieve the types of range that many LiDAR systems need. But one thing to note here is that in terms of the supplier availability for VCSELs, there's a large number of suppliers for near-infrared VCSELs, but only one out there for shortwave infrared. And so the relevance to the wavelength debate, aside from the ecosystem availability, is that higher power lasers can lead to thermal issues requiring cooling. And what did we say earlier? It was that with the shortwave infrared lasers, you can actually output a higher power, but that higher power can lead to thermal issues. Also, shortwave infrared lasers, due to those semiconductor physics that we discussed earlier, have to be built on indium gallium arsenide phosphide, whereas near-infrared lasers are gallium arsenide. Gallium arsenide on its own has larger wafer size foundries, whereas gallium arsenide alloyed with indium phosphide, the wafer foundries are smaller, and as a result of that, each chip will be higher cost. Now let's talk about the eye safety considerations of the different wavelengths that we've been talking about. LiDAR systems obviously emit light, which can hit people in the eye, and as a result of that, we have to be mindful of eye safety. In fact, as was described earlier, we use very short pulses in LiDAR systems with a high amount of peak power. And that's spread over a wide angle of view, while the human eye has a limited angle of view, but there will still be some overlap. And so there is a specification called IEC 68025, which describes the eye safety limits, specifically the maximum permissible exposure for a 1 nanosecond laser pulse across the wavelengths. And as you can see, at the near-infrared wavelengths, for example, at 905, you're at 1 times 10 to the power of minus 6, whereas at 1550 nanometer, you're at 1, and the units are in joules per centimeter squared. So that's 6 orders of magnitude difference in terms of the allowable laser power. That doesn't mean that you're going to actually output that much power if you were operating at 1550 nanometer. It may just not be feasible, but you have a lot more headroom to work with. So what's important is that we design these LiDAR systems properly. So the laser pulses can be shortened to reduce the energy per pulse. And if the laser aperture is increased, then the light leaving the LiDAR system is over a larger area, and as a result of that, you're going to have a lower joules per centimeter squared value. So for an eye-safe design of a near-infrared based LiDAR around 905 nanometer, I'm showing you 3 curves here that are giving different apertures and different pulse widths. So keys to eye-safe design. Shorter laser pulses. You can see that decreasing the pulse width from 4 nanoseconds in the orange line to 1 nanosecond in the blue line with the same aperture gives us a higher amount of maximum peak power that's allowed, which means that we can range further in our LiDAR system while still being eye safe. The other thing we can do is increasing the laser aperture size. So increasing that optics aperture to 5 millimeters in the gray line there compared to the blue line having been the 2 millimeter increases our maximum peak power allowed for a 30-degree angle of view by a factor of about 6. So that's what's important here. It's important to design the LiDAR system with eye safety in mind. But we should also note that for the same amount of laser power being output, if we have a better, more sensitive detector, we can sense lower signals, which means that we can achieve longer range with our LiDAR system, or we can see darker objects, lower reflectivity objects at a further distance. And that brings me to the next topic, which is going to be system performance and cost. So now I want to show you how at SensL we've been building better detectors to enable better LiDAR systems. On this graph, I've got photon detection efficiency on the y-axis, which is a key metric to describe detectors that says how sensitive they are. 4 years ago, our detectors were at about 1.5% PDE at 905 nanometer. And then we started developing a red-sensitive process. So we started doing things to the silicon to make its responsivity to the higher wavelengths of light go up. And we went to 3% in 2017, 7% in 2018. With our RD series, we were at 10%. And this year, we've achieved a photon detection efficiency with our latest RDM series of up to 18% efficiency. Now we should also note that there's a different metric there under PDE called crosstalk. And you can see that that's been decreasing from 30% to 25% even as the photon detection efficiency is increasing. Crosstalk is a form of noise and we want to keep that as low as possible. So we're not stopping there. In the next couple of years, we'll be moving to increase the PDE by another factor of 2 while cutting the crosstalk in more than half. And what that means is that we're going to be getting better detectors with higher photon detection efficiency, lower noise, a faster recovery time, and these will be automotive qualified products. So the system impact at the end of the day of increasing PDE, again, is longer range or being able to use a lower laser power for the same range. So we talked about the detector performance enough. Let's now look at the system performance. What I'm going to be showing you now is a ranging performance comparison of a shortwave infrared system and a near-infrared system based on a 16-element detector array that's going to have a laser line and beam steering to go across the horizontal field of view of the LiDAR system. And the metrics we're going to use for the two types of systems are a 905 nanometer system that conservatively gets a detector photon detection efficiency of 15% with a laser power of 800 watts across the small slice angle of view. Whereas with the 1550 nanometer system, you have detectors that have a much higher efficiency, and so you have a 50% detector PDE. And you can use a higher laser power that's still eye safe. You can use 2000 watts in this case. Now, we're going to use identical parameters for everything else in this system simulation in terms of the optics and the bandpass filter, but we're going to obviously use real metrics for the ambient photons that exist at 1550 nanometer versus 905 nanometer. And when I show you the simulation, it's important to note that we validated this simulation model with a NIR LiDAR system, a hardware demonstrator that we built. And if you're interested, you can look at the paper, which describes the simulation model in addition to the performance of the hardware demonstrator and how well they correlate together. Now, when we use that simulation model with these parameters, we see that indeed the shortwave infrared system ranges further. It goes to about 500 meters for a 10% reflectivity object. But having said that, the near-infrared system with a 15% PDE detector still gives you well over 200 meters of range for a 10% reflectivity object. So both of these systems meet automotive long-range requirements in good environmental conditions, so that being beyond 200 meters. Now, we talked about the water absorption properties of the shortwave infrared wavelengths. So what's the impact of unfavorable weather on LiDAR performance? Well, that water absorption effect should come into play here. And there is a study comparing a 900 nanometer versus a 1550 nanometer rangefinder's performance in adverse weather. And that showed that the 1550 nanometer based system degrades rapidly in cases of rain with 2 millimeters per hour. That's just light rain, and you had worse performance with the 1550 nanometer system. And in the case of 25 millimeters per hour, you had a drastic difference. All of that is to say that 1550 nanometer based systems, of course, can increase the laser power to compensate, but there's going to be a thermal trade-off. Now, this isn't an exact comparison of LiDAR systems, but a single point rangefinder, as shown in this study, can be analogous. Now, I wanted to show one additional thing here, which is that using that system that I described earlier, the hardware demonstrator that we built for validating the simulation model, we captured a video of a vehicle moving through a tent with fog. And as you can see here in the video, as the vehicle moves through the fog, you can actually see the car beyond the fog using the LiDAR system based on 905 nanometer. And this is just to show that a near-infrared based system can actually penetrate through the fog and sense objects on the other side. Now let's circle back to the cost considerations of the great wavelength debate. So we've talked about the fact that on the detector side you have silicon CMOS-based detectors that are going to be lower cost, and you have larger wafer size foundries for the emitters that are again going to be lower cost. But there was a report from IHS Markit that put numbers to this. And when you compare a LiDAR system in 2019 for shortwave infrared versus near-infrared, you see that the component costs for the detector and the emitter were anywhere between 10 to 100 times higher. And even in 6 years, with the additional volume that may come, you're not getting the cost downs to the same level that you are on the near-infrared side. So with shortwave infrared in 2025, you're still looking at a per channel cost of $155 based on this report. So if you have a 64 channel system, obviously you multiply that by that many times. Having said that, the market dynamics themselves also don't favor shortwave infrared. You've seen a push out of autonomous vehicles, of level 4 and level 5 autonomous vehicles, which were forecast to be on the road by 2020 or 2021, 3 to 4 years ago. And now that's been pushed out to closer to 2025. And that means that the ramp for LiDAR is going to be pushed out. And in the meantime, the industrial and robotics markets, which do require LiDAR, actually need shorter range systems, which is not a benefit of shortwave infrared. Remember that a key advantage is being able to do longer range. And these markets are more cost conscious. So when you hear that shortwave infrared can achieve the cost targets when the LiDAR market ramps, Well, if you can't offer the cost targets to the LiDAR market for those applications, then you're not going to be able to fill those fabs and get your costs down. So it's a circular argument that ends up not being able to work. So have we settled the debate here today? Well, we've seen that the vast majority of LiDAR manufacturers use near-infrared wavelengths. We've also shown clearly that the cost and availability of the ecosystem are key factors, and near-infrared systems will always be cheaper due to the technology advantage and the economy of scale. And despite the fact that shortwave infrared does provide longer ranging performance in ideal conditions, and there's no doubt about that, near-infrared LiDAR can meet all automotive requirements of short-range and long-range LiDAR. This is why near-infrared-based LiDARs are being commercialized first for the automotive mass market for passenger vehicles starting in start of production 2021 and also in autonomous driving. So the picture is becoming clearer, but the debate will still march on while the market continues to mature. And with that, I'd like to thank you for listening to my talk. And if you have any questions, you can contact me at the email address listed on this slide.